We're going to be talking about speed and velocity and the difference between the two. So let's just dive right in. Speed is how we measure how fast something's moving. It is a change in distance over time. You can think about the rate of change of distance with respect to time. We measure it in meters per second if we are doing SI units, but obviously we could measure it in any length over time. We could have miles per hour, kilometers per minute, or anything that we really want to. But our SI is meters per second. Speed is always a positive value. Think it doesn't really make sense to have negative speed. You can either not be moving or you can be moving at some speed. And then the average is not the same as instantaneous. What's the difference between the two? Well, this is how the average speed is a distance over time. If I travel, think of it 100, I think I go 100 miles, and that takes me 2 hours to do so. Well, what would be my average? Well, that'd be on average, I was traveling at 50 miles per hour. Does that mean at every single point along the way, I was going exactly 50 miles per hour? Think about like when you're on a highway traveling at some speed. Well, you can speed up and slow down at some different degrees. An average is just the sum of all of those instantaneous speeds. Instantaneous then means like at a particular point, maybe my speed was 46 miles per hour. Maybe at another point, my speed was 55 miles per hour. It can be larger or smaller than the average at any given point. Instantaneous means speed at a very specific moment in time. Average is over a period of time. So here's a couple practice problems for you. I would encourage you to solve or to pause the video and try solving a couple of them. Probably help you if you had answers, and you will see the answers here now. Answers to those problems. Now, let's talk about velocity. How is it any different than speed? So velocity is also a measurement of motion, but it's different than speed because it is our rate, so similar to speed, rate of motion, how quickly something is moving, but it includes facts about direction. It is measured in meters per second. Because it has both a magnitude and a direction, makes it a vector. So the sign gives us a positive, or the sign gives us the direction, positive or negative. This is for 1D motion, but we could also have vectors, just like we've learned. So I could also have motion maybe like this, at a certain angle of 20 degrees, or what have you. And similarly to the average speed, we have average velocity is displacement over time, delta x over t, instead of just the distance. So let's start with a 1D dimensional or one-dimensional problem where an athlete sprints 50 meters in 4 seconds. So it goes forwards 50 meters, then walks slowly back to the starting line. So then comes backwards another 50 meters, and then that takes 40 seconds. So 50 meters forwards in 4 seconds, and then walks back to the starting line in 40 meters. If we take the direction of the sprint to be positive, it means this way is positive and this way is negative. See if you can come up with solutions to average sprint velocity, walking velocity, and velocity of the round trip. Go ahead and pause the video and see if you can figure it out. All right, our answers should be 50 over 4 will give us 50 over 4 will give us 12.5 meters per second. And then if we do 50 over 40, well, that's going to give us 1.25 meters per second. Think to ourselves, positive, because we went forwards in our sprint, then it has to be negative 1.25 meters per second because we went backwards for our walk. What's the average velocity? 0 meters per second. We ended up right back where we started. So there was no average velocity at all. Another example, Britta Steffen of Germany set to win the women's Olympic record for the 100-meter freestyle swim with a time of 53.12 seconds. What's your average speed in meters per second? Easy. Make a unit conversion to convert that to miles per hour. Go ahead and pause the video and see if you can figure it out. Our answer should be 1.88 meters per second or 4.12 miles per hour. Now, let's take a look at what data would look like graphed. This is going to be our first introduction to like getting some graphs going on in physics, and we will continue to do this for the entirety of the year. How can we show the motion of an object as it moves through time? Think about if I have different, I have this data here that's marking I'm at a different position in my x direction So I could start here 0, 0, and at some time later I might be at 20, and I have very specific measurements of each second me moving to different locations. How would it make sense to plot this information? Well, what we are doing is making a position versus time graph, where we have position on our y-axis and time on our x-axis. We can test each one of them. We start at 0, 0. At 1 second later, we are at 4, and then the rest of our data is also shown here. Think about what this graph alone, like even if I don't have the table, what does this graph tell us? What are we doing from 0 to 5 seconds? Well, we seem to have a commonality. It's going to be the best straight line I got. Amongst these points, we have a pretty straight slope going on. And what are we doing from 5 to 8, this point? And then what are we doing from 8 to 13? Well, we are moving forwards. And then what are we doing here? We are at rest. And what are we doing here? We are moving backwards. And we know that because we start at 20 and then we move back to 10. So we are moving first forwards, and then we stop, and then we move backwards. That's what's going on in this graph. Is there any more information I could get from here? Actually, for sure. So we just saw this position time graph. We got position is always our y, time is always our x. And so let's see two different things graphed here. Here we have a motion of a red car and a blue car. And I think one of the easiest things to forget for a position time graph is that it's for linear motion. We're never going to graph on a position time graph 2D motion. But we get like 2D graphs, it's easy to get confused with vectors. We're not dealing with vectors here. We are showing how an object's linear position changes. So it only has one dimension to move in, the x dimension. And we want to show how that changes with time. And our blue car is just beep bopping along. Every second, it's just moving a little bit. It's moving at a pretty constant speed. But then out of nowhere, the red car comes in and is moving much faster. And so notice do we know from this graph? What are some things we can get from here? Well, we can see there's an intersection. That's always an interesting point on any graph. And this is where the two are at the same place at the same time. This happens to happen at 7 seconds for this graph. We see that initially the blue car starts off at 20. When our time first started, the blue car was at 20. And we didn't even see the red car for 4 seconds until after 4 seconds had passed. And then the blue car started behind the red car. Like when it first came in, it started at 0. But it did not take long for the red car to overtake the blue car. And then after 7 seconds, we see the red car is in front of the blue. It has a higher position when we end than the blue car does. We can see that on the position graph over on this side. Two more really big things that we can tell from a position time graph. And this is any graph that we look at, we have an independent versus dependent variable. What's dependent variable changes when the independent changes? We have the y versus the x. We can get similar ideas about what is object A doing, what is object B doing. We see object A is not moving as quickly as object B does. Object B starts behind A, but similar thing happened as in our last graph. At this point in time, like 1.7, 1.8, the two objects are at the same place at the same time, and then object B is going ahead of A. So we know B is traveling faster than A is. And we can tell that easily because B has a higher slope. And so what do slopes tell us about a graph? If it is positive slope, it means it's moving forwards. We can see that with both D and B. They both have positive slopes. Both are moving start at a small position and are moving forwards in our x direction. This is like 0, maybe call that 5, maybe call that 10. They are moving forwards in the x direction. Negative slopes, so like the blue line of A, are moving backwards. Here we start at 10, and as time goes on, we are going backwards on our graph. And then a horizontal line like C, no motion. What is C doing? It is staying at a constant 5 over this whole time. And we have times down here. And we can ask yourself, like at 1 second, where's C? Well, it's at 5. At second number 2, where's C? It's still at 5. Still at 5, still at 5. It's not moving anywhere. So horizontal lines are no slope. And more so than just the shape of the slope, whether it's positive, negative, or horizontal, we can also get an actual velocity from the rise over the run. And think, slope is just rise over run. On a position time graph, if I have this slope and I have, think slope is just rise over run, y over x. Well, what is my y here? Well, that's my change in position. So my displacement over a certain time. And so y, rise over run, and we get a velocity is, why is this change in v? This velocity should be delta x over t, just the same as our other equations where it is a displacement over a time. Do not get confused either that delta x over t, this is kind of confusing, that displacement is always delta x, but we happen to be graphing our position on the y, not the x. So this all over here, our position is over here. And so our motion in the y direction is actually our delta x. And then our motion in the x direction is our time. Please don't get confused with those two variables. So how do we use this to calculate some velocities? Oh, I need to do them. So go ahead and pause the video and see if you can figure out these answers. Our answer to the first one should be 6 meters per second. Our answer to the second one is 0 meters per second. Our answer to the third one is negative 25 meters per second. And our answer to the last one is 0 meters per second. All right, and then so a position time graph overview. Again, just going over, a big slope has a fast constant velocity. Here for our red line, we have a constant velocity and then a 0 velocity, and then we switch to a negative velocity. And then anytime we have a curve on a position time graph, what's this showing me? Showing me that my slope is changing and it's getting higher and higher and higher. When we have a changing slope, that means we have a changing velocity. And when we have a changing velocity, we have acceleration, which is going to be our topic for next time. See if you can create a position time graph based on the following information. I do not have an answer for this one, but you can still see if you can do that. And then same thing with this one. See if you can make a position time graph based on this information. And then here we have a train moving slowly back and forth. During which portion does this train have the smallest speed? Notice I have smallest speed. Which one do you think that might be? And then that is it for today.